Okay, so let's proceed. So the plane wave equation, it will have a plane wave factor, the usual things, and then of course something needs to carry this mu index, and this is the job of the polarization. So this is what epsilon mu p is there for. And now if this is to solve that equation of motion with these gauge conditions, so if this is to solve the equation of motion with this subjected to these gauge conditions, then we have to sort of figure out what does that mean. So one thing that it means is that p square is equal to 0. As you know, it's an on-shell condition. And the gauge condition means that epsilon 0 has to be identically 0. And p dot epsilon, the 3 vector, that has to be 0 as well. Okay. Now, as it's standard for massless particles, you can always choose an on-shell momenta which looks like this. So the time-like component, and then you can give only one of the space-like components the equal things. So this is basically a electromagnetic wave moving with energy E in the z-axis, along the z-axis, right? So this is one choice. And corresponding to this, I can find a pair of, so now you see that this vectors, even though there are 4 of them, they have to satisfy 2 conditions. So there are only 2 which are going to be independent. So you can solve for them, and there's no unique solution. So you can find one solution like this. Epsilon 1 is this, and epsilon 2 is this. Or you can find another set of solutions. Epsilon 1 will be 1 over square root 2, 0, 1, I, 0. Epsilon 2 will be 1 over square root 2, 0, 1, minus 1, 0. So those of you who have studied optics or electromagnetism might have known these things as linearly polarized light, and these are circularly polarized light. Okay. But now the point that I want to make is that note that this epsilon mu of p, this, despite having a mu index, this cannot be a Lorentz 4 vector. And the reason it cannot be a Lorentz 4 vector is because this condition has to be true always. That zeroth component is always 0. And that is very hard to ensure for a vector, because even if you give me a vector whose zeroth component is 0, I can just do a boost and make it non-zero. If it is to be 0 in all reference frame, then whatever this object is, this is definitely not a Lorentz 4 vector. And in fact, indeed, one can see that under general Lorentz transformation, epsilon mu of p, this has a piece which transforms as if it was a tensor, it was a vector, but then there is some term which is proportional to p mu. Okay, this hash is some number which we don't care. I mean, you can of course figure it out. I'm sure some of you may have already seen this thing. If not, this is a good exercise to, you can, if you want, you can just start with one of these things, try to do a Lorentz transformation and see this out explicitly. Okay. Now this has some very interesting consequences that epsilon 10, this polarization does not transform like an ordinary vector. So this has a very important consequence, which is what we are going to see now. So the consequence involves looking at a process, any QED process, where at least one external particle is a photon. Okay, so this could be some complicated scattering involving lots of electrons, positrons, there could be other photons. We don't care about the other external particles. And we don't want to care about which order of perturbation theory is this in. All we care about is the fact that there is one external photon. So this is a scattering with at least one external photon. So for such a scattering, the total amplitude, the Feynman amplitude, this I can always write as some epsilon I mu times some m mu. Okay, because there is remember the Feynman rules that we derived last time, that if there is an external photon, and let's take this external photon to be incoming, doesn't matter incoming or outgoing. If it's outgoing, you can put an epsilon bar. So that will always contribute a factor epsilon I mu, and rest of the diagrams using the Feynman rules, whatever that is, that has to have one mu free index so that there is a contraction, because the full amplitude has no indices. And in fact, we know that this is supposed to be Lorentz invariant. This is supposed to be scalar. And this thing that we compute from the other Feynman rules, this has to be a Lorentz 4 vector, because this mu index can come either from the propagators, or which is the eta mu news, or from the vertex factors, which has gamma mu's, right? So all of them transform like a Lorentz 4 vector. So this thing has to be a Lorentz 4 vector. And now you see we are in a sort of a weird situation, because this is supposed to be Lorentz scalar. This transforms like a Lorentz 4 vector, but this guy does not transform like a Lorentz 4 vector. And in fact, we have already written down how does it transform. So under a general Lorentz transformation, under some Lorentz transformation, this m goes to, so Im goes to some Im prime, and this will be some epsilon mu m mu, because remember the first term transformed like a lambda mu nu, so that is going to be that is going to be invariant, but then there is going to be some number times p mu m mu, right? So this means Im prime is Im plus this some number p mu m mu. And now the only way this is consistent is if this guy is identically zero. It has to be. There's no other way to make this thing consistent. So the only way this is consistent is if p mu m mu is equals to 0. This is a super important identity, which is called a Ward identity. And it's not specific to QED. Ward identities can be there for other kinds of quantum field theories as well. But it's definitely for QED, it takes this specific form. Okay. So this identity has profound consequences. So first consequence is the fact that when you want to sum over photon polarizations, this identity will help us in sort of figuring out that how to sum over photon polarizations. And this is something that we will explicitly see in, let's say, half an hour. And this is because this is what we will need when we compute the scattering amplitudes, or particularly the unpolarized scattering amplitude. But this has another profound consequence, which is that this actually implies in a very nice set of argument that the electric charge has to be conserved. So let's discuss this first. Okay, so charge conservation. So to discuss charge conservation, we need to first look into a very specific kind of Feynman diagram. So, or a process. The process looks like this. So we have some complicated process going on at some arbitrary loop order. It doesn't have to be tree level. So there are lots and lots of external particles there could be, and this could be fermions, this could be positrons, and some of them even could be ordinary photons. What we only demand is that on one of the external legs, only one of them, there is another external photon that joins in via the usual vertex. So this has to be a fermion line, right? So this is a fermion line, and there is a photon that comes in, and then it joins in, and then it goes through. Okay, and then this external photon has a momenta, which I'm going to call Q. And this diagram is, this Feynman amplitude is something that I'm giving a name M1. Now it turns out that this diagram has a very nice relation to another diagram, which is exactly the same one, except this external photon leg has now been removed. So it's exactly the same process without this external photon with moment q. And that, let's call it M2. And the relation between these two is by looking at the limit where q mu is taken to be very, 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 very weak. So this external photon has extremely low energy. And this particular limit has a name. It's called a soft limit. And the photon which has a momenta which is soft is often called a soft photon. So let's take this soft photon limit, which is what was considered first by Steven Weinberg in a very famous paper, I think around 1965. So in the limit q mu tends to 0, what Weinberg proved is that this amplitude M1 can be written as M2 with the nth external leg, the leg where the soft photon is attached, that leg factor replaced by something called a soft factor. So we'll see what that soft factor is for QED. Okay. So let's focus on fermions. So if I have, let's say, the nth external leg like this one, imagine that that was a positron. So M2, I can think, is some US bar P times some M. Okay, so I'm just looking at M2 now, this one. That this is a positron. So this positron comes in. So there is some factor, which is the external leg factor for incoming positrons. And whatever the rest of the diagram is, I'm just calling it M. Okay, I don't care about the details of the rest of the diagram, just calling it M. So M is essentially everything apart from this leg. So M is everything here. That's it. Okay. On the other hand, I can do the same thing for M1, the diagram on the left-hand side. But now you see the nth factor, nth leg, is not just an incoming positron. It's an incoming positron. So, sorry. It's an incoming positron, a soft photon, and they combine together and they become an incoming electron, and then they enter this rest of the diagram. Okay. So that is something we can also write down by the Feynman rules. So we have the US bar P for the incoming positron, then the vertex factor, which is IE gamma mu, then the polarization for the incoming photon, which is epsilon mu of Q, and then the internal line, the propagator for the electron, which is I P slash plus Q slash plus M divided by P plus Q squared minus M squared plus the Feynman I epsilon. And then the rest of the diagram, which is the same as the one for the M2. So that's M. So we can simplify the denominator easily, right? The denominator is P plus Q whole squared minus M squared. If you expand it out, it's P squared plus Q squared plus 2P dot Q minus M squared. Now remember, the electron is on shell, so P squared equals M squared, so that cancels. The photon is on shell, so Q squared is equal to 0. So the only term that remains is the twice P dot Q. Okay, so that's one way of one simplification. The other simplification comes from the fact, essentially, that you can sum over the spins, right? And then use the completeness relations that U S of P, U bar S of P. This is P slash of plus M, and U S P, gamma mu US prime, P is twice delta SS prime, P mu. So when you use this relation, you can actually write down something which is quite remarkable, that this M1, in fact, let's call this M1 everything other than epsilon mu. So I'll write the M1 as epsilon mu Q M1 mu. So everything other than the epsilon mu, I'm calling it M1 mu. So this M1 mu factor is going to be some number, which I'm not being very careful about, and it's not going to be super important. E times P mu, P dot Q plus I epsilon times M2 mu. And this factor is usually sort of given just one name. So I'm going to call it F1 mu. And this is a factor that depends on P, Q, and the polarization epsilon times M2 mu. Okay. So this factor F1 mu, F1 is just this this P mu by P dot Q plus I epsilon, that thing. That is what is called a soft factor. Okay. Now you have to consider the fact that this soft photon, so we just looked into the amplitude that the soft photon essentially emitted from the nth leg, but it doesn't have to emit from the nth leg, right? It could emit from the soft photon can emit from any of the other external legs. And these are all same order in perturbation theory. So we have to sum over all the Feynman diagrams to get to the full result. So the full M1 mu, let's put a hat, that would involve us summing over all of this. And when we sum over this thing, the only thing we need to be careful about is that whether this electric charge is going to come with a plus sign or a minus sign. And whether it's going to come with a plus sign or a minus sign, it's going to depend on two things. One is that whether it's a positron or an electron. And the second is that whether it's incoming or outgoing. Because incoming, outgoing, why does it matter? Because the momentum will flip. If we'll adopt the convention that incoming momenta is positive and outgoing momenta is negative, let's say, then that's the reason. Okay. So let's just simply say that for each electron or positron for nth external leg, depending on whether it's electron, positron, or whether it's internal or incoming or outgoing, there's a sign factor. So I'm going to just simply write it as sign of En. And En means that the nth particles, okay? And then, of course, En itself and the Fn mu of the Pn momenta, soft momenta, and the polarization. And then this whole thing has to contract with M2 mu. Okay. So this is a fully general expression. And this, in fact, this is such a general expression that it is called a soft photon theorem. And this theorem actually holds for arbitrary external matter without any spin. So we derived this particularly for fermions, but it doesn't have to be QED. There are better ways of deriving this thing which doesn't necessarily invoke any specific matter action. And this form of the thing is still true. Now, essentially, you see that we can use the Ward identity. What does Ward identity say? Because M1 mu is a process where there is one external photon leg, right? So it's a kind of diagram for which we can use Ward identity. And it says that if you take this M1 mu part and you take its contraction with the momenta of the photon, which it has, the external photon, then this has to be 0. So that's what Ward identity said. But now here you see, if you take Q mu with Fn mu, right? Then this is essentially your Q dot P by Q dot P plus I epsilon. So the I epsilon factor is there for the normalization. But here I don't need to do regularization anymore. I can just drop this, and this is essentially just 1. So Q mu M1 mu, this boils down to summation over n sine of En multiplying M2 is equals to 0. M2 some nu or something. Okay. But then the point is that none of these M2 components are 0. So M2 is not 0. So then the only way this is true is if this guy is 0. But what is this guy? This guy is simply counting total change of charge. So it counts total incoming electric charge plus plus E for the positrons minus E for the electrons. And then it counts the total outgoing charge. And then it says that the total outgoing minus total incoming, this is 0. Or in other words, charge is conserved. Okay. So this way of proving charge conservation is actually fairly general. And it essentially says that any unitary QFT which has massless spin 1 boson, they will always couple to matter that conserves charge. Okay, so this way of proving charge conservation using word identity, it actually is very general. It works for even if you, let's say, change the dimensions. If you don't like 4 dimensions, you're going some higher dimensions, it's perfectly universal. But specifically in d equals to 4, there's a way to relate this word identities, which is a very relatively recent result, to what are called asymptotic symmetries or large gauge transformations. So if some of you know these terms, then it's fine. If you don't know these terms, don't worry. This is not going to be important. But this way of connecting the charge conservation to this symmetry, is very specific to d equals to 4. There are some partial results which is almost as good for even dimensions. But for odd dimensions, it's completely open. So we don't know how to relate word identity with some sort of large gauge transformations. But the proof based on word identity, the one that we discuss here, that is independent of any dimensions or whatsoever. That's a very general derivation. Okay. So the conclusion is that you have no choice. The moment you decided, or the moment you realize that experimental data tells us that electromagnetic wave has to be captured by the quantum version of it has to be captured by a massless spin 1 boson, the charge conservation was almost, I mean, it was inevitable. It had to be there. Okay, you couldn't couple it to a matter in a consistent way without having charge conservation. Okay, so that's what I wanted to say about word identity and charge conservation. If there is any specific...
Sir, what is that? D equals to, it goes to 2n and D equals 2n plus 1, almost open.
So that's the thing that I said, that this specifically in D equals to 4, this word identity could be related to what are called asymptotic symmetries or large gauge transformations. So in D equals to 4, you can think of that the charge is conserved because there is some symmetry at the spatial infinity, like not in any finite position, but if you take the limit, if you go into the edge of the universe, there is a special symmetry which are called asymptotic symmetry. Because of that symmetry, charge is conserved. You can think of it like that. But that's something that is D equals to 4. In higher dimensions, it's the proof doesn't quite extend as naturally. I'm not saying that it's impossible. It's just that nobody knows yet. So for even dimensions, there is almost a similar version. So for 6, 8, 10, let's say. But for odd dimensions, it's completely open. Nobody knows how to do that. But what I said now is that the proof that I outlined here, which just uses word identity, it doesn't use any asymptotic symmetry or anything. That is fairly general. That does not care about 4D or anything, any such thing. You can just prove it. And even this is independent of perturbation theory. This is an exact non-perturbative result.
And of course, we used here D equals 4. So we just used
We did not use D equals to 4. Nowhere did I use the information that D is 4, right? I never used see all of these mu indices, right? If they run over more values rather than 0, 1, 2, 3, none of this derivation will go wrong. It will still work through.
Okay. All right. Okay. Got it. Thank you. Thank you.
Yeah. Any other questions for word identities or conservation of charges? Because this is the natural place to ask. We will be moving on to computation of a scattering amplitude next. So this is a natural place to ask questions, particularly for the things that we discussed so far. Okay, so I guess not.
I'm sorry.
Yes.
I just had a
Mhm.
open question. We finished last lecture on Feynman diagrams, and then today we started off with photon polarizations. I'm just trying to connect the two, sir.
Well, photon polarizations are definitely parts of the Feynman rules. So we ended last lecture in deriving the Feynman rules, and now we are using the Feynman rules. So we have used the Feynman rules to write down these factors, right?
Right.
How did we write?
have those
How did we write these
M-
things down?
Those. Yeah.
Yeah. So we are making use of Feynman rules now.
Okay, and we are specifically applying it to the QED scenario where you have two polarizations of entering.
Yeah, I mean, so first is that I showed that the Feynman rules, in particular, the fact that the external photon will have this polarization thing, that it's not a vector, even though it has a mu index, and it's not a vector in the sense that if you do a Lorentz transformation, there's a part that transforms like a vector, then there is a part which is proportional to the moment of the photon. And that implied that any amplitude, any scattering that has one external photon has to satisfy an identity like this, which is called a word identity. And then this word identity is extremely super important for any Feynman diagrams involving QED. So I pointed out just two applications, right? One of them is charge conservation, which is what we discussed. The summing over photon thing we are going to see in a short while. And then the charge conservation we derived by looking at a very specific diagram. We said that, okay, I mean, consider there is some QED process with lots of protons, electrons going on, but at least one of them has an external photon with a momenta which is very, 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 very low. And then Steven Weinberg proved a theorem where that can be related to exactly the same process without this external photon leg. And the way the relation works is precisely the way it is written here. And that through word identity has a direct consequence that the total charge has to be conserved.
And of course, we concluded that the moment we decided to do that, the charge conservation was inevitable.
Yeah, I mean, none of this thing, I mean, at this point, I mean, so as I said that, I mean, there is a way to derive the same expression or rather this expression without using any of the details of the Feynman rules. So it is not sensitive on the specific Lagrangian that you start off with. The only thing that matters is that the photon is captured by something which is a massless spin 1 boson. So there are two polarizations. That's the only thing that matters. And then you can just, of course, the proof also works. You can conclude the same. So that's what I said, that like, so this theorem holds for arbitrary matter and arbitrary spin, and the proof is something that works fairly generally. And then this is the comment that I had, that this is unavoidable. Anytime you have a unitary QFT with massless spin 1 bosons and you want them to interact with some matter, whatever matter that you turn on, whether they're fermions, complex scalars, whatnot, they will always have to be something that conserves electric charge. I mean, conserves some charge, which we call electric charge, as simple as that.
So any interaction of a massless boson with another particle, there will
Yeah.
be
Yeah.
conservation of charge.
So those matters will be charged, and those charges will have to be conserved.
Okay, thank you. Can you just a little bit detail that soft factor? Can you just go over that? F soft factor a little bit if you scroll up a little. Yeah, that F1 mu.
So this thing is F1 mu. For QED, this is what it is.
Okay, thank you.
Mhm. Okay. So let's move on. So our focus is going to be on 2-to-2 scattering because that's the most important thing. So what does that mean? It means that you have two particles that are coming in with momenta P1 and P2, and two particles that are going out. The two particles coming in, they collide with each other, and then two particles go out, whose momentas we are going to take P3 and P4. And I'm sure all of you have seen these things before, but just for at least convenience and setting up the notations, let me set it once more. So in these sort of situations, there is a nice combination of kinematic momentas, which is useful, are called Mandelstam variables. So these are called S, T, and U. So S is defined as P1 plus P2 whole square, which of course by momentum conservation is same as P3 plus P4 whole square. Then T is P3 minus P1 whole square, which is same as P4 minus P2 whole square. And then U is P4 minus P1 whole squared, which is same as P3 minus P2 whole square. Okay, so these are called Mandelstam variables, S, T, and U. These are all Lorentz invariant. And I'm sure all of you have proved this identity that S plus T plus U is equals to sum over the mass squared of each external particle. Okay, so if you have proved this identity, fine. If you have not proved this identity, you should absolutely do it. And as I said, that we are going to work with the convention that incoming momenta will have positive sign and outgoing momenta will have negative sign. Now, whenever you have a 2-to-2 scattering, so two particles scattered to two particles, and that involves exchange of one internal line, so one propagator, or okay, so one virtual particle if you want. Then the Feynman diagrams can be of at most three possible types. And these types are usually given a name. They are called channels. So the first one is like this, that P1 and P2 meets at one vertex. It becomes some internal line, which I'm calling here alpha, and then P3 and P4 lives. So this is what is called an S channel. Why is it an S channel? Because the amplitude will be proportional to 1 over S minus whatever is the mass of the virtual particle squared. Yeah, because alpha here will have momenta, which is going to be equals to P1 plus P2. So here the internal line is going to have momenta P1 plus P2, which is precisely the thing that you need for S, P1 plus P2 whole squared. Then you can have something which is this, that P1 and P3 meets at one vertex, and this is called T channel, for the same reason that the amplitude will be proportional to T minus M alpha squared. And the other possibility is what is called an U channel. Okay. For the same reason that M is going to be proportional to U minus M alpha squared. So I'm sure all of you have seen this thing, but it's good to just refresh them once anyway. Okay. So now the specific QED scattering that we are going to be focusing on today is called the Compton scattering. All of you have heard of this scattering for sure, but we are going to look at it in a QFT perspective, not the standard relativistic kinematics perspective, which you may have seen already in your undergraduate courses. And this scattering process is precisely when an electron collides with a photon and another electron and another photon goes out. Okay, so it's usually written like this, that E minus, so gamma stands for the photon. So E minus and gamma comes in, they collide, and another electron and a photon goes away. The reason we are going to discuss this thing is probably among all the textbook QED scattering, this is the one which is more involved. So it's good to discuss the more involved ones, and then the easier ones you can try to work it out for yourselves at home. So what are the diagrams that are going to contribute for this? And of course, we are going to look at only tree level because this course is designed for only tree level QFT. So at tree level, there are going to be one diagram, which is this, which is what we could have called the S-channel diagram. So the pink wavy line, remember the wavy line stands for the external photon, and the solid line stands for the electron or the positron. Okay, so here, of course, we are going to think that there is an electron that is coming in, there is a photon that comes in, they join together in this vertex, there's a positron that comes out, and then it splits into another electron and another photon that goes out. Okay, so we are going to give the incoming electron the momental level P1, the incoming photon the momental level P2, outgoing electron the momental level P3, and the outgoing momental level for the photon P4. So this is one possible diagram. What is another possible diagram? The other possible diagram will look something like this, that the electron comes in, it splits into the P4 photon which goes out and the positron which then gets absorbed by the incoming photon, and then it gets converted into an electron which goes out here. So this is what we have called the U-channel diagram, right? This is the P1 minus P4 combination. And the point is that I'm going to sort of tell you that these are the only two diagrams that is going to contribute. So you might say that, okay, what happened to the T-channel? Because there are three possibilities that I just discussed in general. Why can't the T-channel contribute? Well, if you come here and try to do the T-channel thing, so if you try to draw the T-channel, the diagram will look something like this, that the P1 has to come into a vertex and a P2 has to emit. Remember P1, so this should not be P2, this should be something P3. So oops. Anyway, so this is something that is P3. That has to go out, but remember therefore this suggests that this is a vertex where there has to be two electrons that comes together. And on the other side, the two photons have to come and join together in the same vertex. But in QED, there is no such vertex. Remember, there's only one interaction term that we found consistent with everything that we discussed. And that always had three legs. One corresponds to electron, one corresponds to positron, and the one corresponds to photon. So this suggests that you need to have a vertex where there are two photon lines and one electrons, or two photons and one positrons, or you need a vertex which are two electrons and one positrons, or three electrons, blah, blah, blah. None of them are consistent with the principles of Lorentz invariance, gauge symmetry, none of it. So this vertex simply does not exist. So this diagram also does not contribute for this particular process. So this is simply impossible. So there are no T-channel contributions for this specific process. I'm not saying that there will never be T-channel contributions in any QED process. For Compton scattering, at tree level, S-channel and U-channel are the only two diagrams that will contribute. Now, whenever you have scattering processes involving fermions, you need to be very careful about the relative signs between the two diagrams. So I wrote here plus, right? And all of you could have, or some of you could have asked that why is it plus, or how did I know is it plus? Because remember, when I interchange the order of fermions, so if I interchange in my weak contraction and canonical way of thinking, if I interchange the order of the fermions, then I should pick up a minus sign, right? So this will become plus if the S channel and the U channel actually have the same fermionic ordering. And of course, you can explicitly write this down in the correlation function, and you will see indeed that they have the same fermionic ordering. So this plus sign is of course correct. But there is a much quicker way of seeing this thing. And the quicker way involves noting that Feynman diagram, the way I have drawn these things, like, two things coming at an angle, going straight, and this has no universal significance. The Feynman diagrams, it's a topological thing. You can just bend and twist as long as you do not tear off a leg or you do not add an extra leg. Anything you do with the Feynman diagram is exactly equivalent. So for example, the S channel, I can just simply draw it like this, and the U channel, I can draw it like this. And then now you see that the fermion lines, nothing is being done to it. The only thing that changes is essentially this P2 and P4 photon, where do they join the fermion lines? Okay, the fermion lines is this vertical green, blue line, and the photon lines are this wavy pink lines. And the only thing that has changed is that when P2 joins in these fermion lines and when P4 emits from these fermion lines, but that is essentially just changing the order of the two photons. And photons are bosonic. So even if I change the order of two photons, there is no sign. So if for the first diagram, whatever sign it has, the second diagram has the same sign. Is this clear? So what I want to say is that both have the same fermionic structure. So the only difference is in the ordering of the photon. So there are no relative signs between these two diagrams. So now all we need to do is that we have figured out that for this scattering process, this S and U channel are the two diagrams. We need to use the Feynman rules to write down the corresponding amplitudes, sum them together to get the total amplitude for this process at tree level. Okay, so we are ready to write down the amplitude. So the total amplitude, of course, IM is going to be sum of two factors, M1 and M2. M1, let's say, stands for the S channel, and M2 stands for the U channel. The S channel diagram is this. So what is M1? So we have to remember M1, M2s, these things are numbers. This has to be some sort of, Lorentz invariant numbers. So it always, you have to keep in mind the structure of the fermions. So in fermions, if you want to get some number, you always have to start with the bar on the left, then whatever matrices comes in the middle, and then the unbarred fermions on the right. So which one among all these four lines will have a bar on the top? Which line will have a bar on its top, according to the Feynman rules that we derived last time? Anyone?
P3 will get the bar and P1 will not get bar.
Yeah, that is absolutely correct. So P3 will get the bar. So I will start with U bar P3, and this could be in some spin state. So I'm just going to call it S prime. And then once you have started with this P3, then the immediate next thing to do is look into the vertex that P3 joins in. So P3 joins in a vertex with photon. So we have to write down its vertex factor. So that's minus, and vertex factor is same for all the possible combinations that we saw last time. So let's call it minus IE gamma mu. This mu is going to contract with the mu of the photon line, which is in the same vertex. And that has P4. And that's an outgoing photon. So outgoing photons in our convention, we said that it's going to be epsilon bar. It's going to have this mu, and it has the momentum P4. And of course, we do not know what is the exact polarization state this outgoing photon is. So I'll just give it some polarization level I. So just like I gave a spin level S prime to the outgoing electron, I gave some polarization to the outgoing photon. Once I have that, now it's the turn of the green line, which is the internal line, and it's an internal fermion line. It's a propagator, and it has a momentum which is P1 plus P2. So this propagator factor is I times P1 plus P2 slash slash plus M divided by this same combination P1 plus P2 whole squared minus M squared. Throughout the rest of this lecture, I'm going to drop the Feynman I epsilon just so, because otherwise we will have not much enough space. But you should all remember that in the denominator of a propagator, there is always a Feynman I epsilon. Is this okay with everyone? Okay, I'm going to assume it's okay with everyone.
Is that irrelevant because it's the normalization factor and it's regularized? Is that why?
It's not because it's irrelevant. The Feynman I epsilon, I mean, if you want to be truly rigorous, the Feynman I epsilon should be there. And only after you've done the computation, only in the end, you should take the limit epsilon goes to 0. I'm just simply dropping it because I don't have space to write all of that. That's the only reason.
Okay.
Expressions are going to get bigger and bigger, and that's it. So someone is saying, I think that would be confusing. Pedro, can you explain why that would be confusing? I'm just simply saying that whenever in the propagator you have something like p square minus m square plus I epsilon, I'm just going to simply write it as 1 over p square minus m square. So whenever you see something, if you're in doubt, just simply imagine that the I epsilon is there. Okay. So propagators, the denominator never comes without I epsilon. It's just, and this is a very standard practice even in while writing research papers, for example, as long as you explain it before using it. Okay, so with this convention in mind, now that we have written down the green line propagator, where does the green line end? It ends on another vertex, right? So we have to write down the vertex factor for the second vertex. So that is, of course, the same, say minus IE. Gamma, but then we have to give a different Lorentz index. So let's call it gamma nu. And what does this gamma nu contract with? It has to contract with the photon polarization. And this is an incoming photon. So this is going to have an epsilon. So this is epsilon nu. And it has a momentum which is P2. And I do not know what polarization the incoming photon was in. So I can give it some different polarization level, which I'm calling J. And finally, there is the incoming electron, which is, I'll just write in the next line, which is U of P1. And it is in some spin state, which I don't know. So I'm going to call it S. Okay, so this is M1. This is the S channel diagram. This is just the mathematical expression for this Feynman diagram. We have another, of course, we have M2.
Is that the amplitude, sir?
Yeah, this is
M1?
the amplitude. Yeah.
Okay. Yeah.
This is just the S channel part. The total amplitude is what I've written upstairs. You have to sum over this two to get the total amplitude.
All right. Okay.
It's the same thing with M2. So we are going to have some U bar S prime P3, then minus IE. This time I'm going to call this one gamma nu, epsilon nu J P2, I P1 slash minus P4 slash plus M P1 minus P4 whole squared minus M squared minus IE gamma mu, the outgoing photon epsilon I mu P4 US P1. So this is M1, this is M2. We are essentially now we are done. All that is left is doing algebra. We have to sum this, square it to get the basically the matrix in the element squared. Then from there, using the standard formulas, you get the differential cross section, blah, blah, blah. So how does one go about simplifying this thing? So now, even before we square it, there is some simplification you can already do. And these are very standard manipulations that one does. So for example, you use the on-shell values of the momenters. So P1 squared and P3 squared, these are the fermion, the electrons. So they square to M squared, which is the mass of the electron. Whereas the P2 and P4, these are the momentum of the photon, so they will square to 0. And that means that P1 plus P2 whole squared minus m squared is twice P1 dot P2, and P1 minus P4 whole squared minus m squared is just minus twice P1 dot P4. Okay, so that's one simplification that you can do in the denominator of both the propagators. So that's one simplification. The other simplification that you can already attempt to do at this stage is to look into the numerator and essentially note that whenever we have P slash plus M gamma nu US of P. So let's expand this thing out. What is this? This is twice P nu minus gamma nu P slash. I'm just multiplying and then plus gamma nu M. Okay, what did I use here? I just simply used the fact that gamma nu is twice delta mu nu minus gamma nu gamma mu. I use this to write the right hand side down. And of course, I have USP. Multiply this whole thing out, 2p nu USP minus gamma nu P slash minus M USP. But remember, USP is something that satisfies P slash minus M. This is the free Dirac equation. So this thing goes to 0. And therefore, this thing just simplifies to twice P nu USP. Okay. And now with these two things, one can actually simplify this considerably. And I'll ask you to just sort of do the 2-3 lines of algebra to see this, and you will get this as the final expression. So in the first line, I have just simply done the simplification. I have written M1 plus M2. So that's all thing written together. And on the second line, all that I have done is that I have just simply written explicitly the first and foremost, the numerical prefactor, which is negative IE squared. That just denotes that which order of perturbation theory we are in, and the I is of course going to be there. And we have just simply written the epsilon bar and the epsilon part separately. And everything else we have just simply wrote as M mu nu. Okay. So this has two mu nu free indices. So this whole thing I have written down M mu nu. And the reason I have done that is that I'll give you today's first exercise is that please check the word identity for this. And what is the word identity for this? That P2 mu M mu nu, this should be 0. Remember, P2 is one of the photon lines. So that should be 0. But I have another photon line, which is P4. And that says that P4 nu M mu nu, this should also be 0. Okay. Okay, so this is the expression for the Feynman amplitude. So what do we do next? Now, typically at this point, the next step is that you have computed IM. We have to now just compute its mod M squared. That's going to be the essentially what is going to give me what is needed for getting the differential cross section. But there is something that is worth considering here, which is of practical utility. And that has to do with the fact that when we computed this M, and from this M, if we compute this mod M square, we have said that the incoming electron has a specific spin state, which we call S, and the outgoing electron has a specific spin state S prime. And both of the photons also have specific polarization states. The incoming photon had a polarization epsilon nu j, and then the outgoing photon had a polarization which was epsilon bar I. Now this is in principle detectable. So all you have to do is that you have to prepare your initial electron and a photon in the specific states. You prepare the electron in a specific state, you prepare the photon in the specific state. And once they scatter, of course, they are going to produce not just a specific state electron or a specific state photon all times. They're going to produce everything because this is quantum theory. But you can imagine that you have built a detectors which only detects if the electron is in a specific state, or it will only detect the photon which is in a specific polarization state. So this is in principle doable. You can imagine doing this experiment. However, in practice, this is not what is done. So in actual experiments, you actually don't have always control over which initial state it is in. It's completely random. So the process through which you generate this initial electron and the initial photon, you do not have such precise control that I'm going to precisely create the electron in this spin state and this photon in that polarization state. So sometimes you might be able to do that, but in general, you are not able to do that. And definitely once we have detectors will detect all possible electrons and photons, irrespective of whatever states they are in. So in actual experiments, if you just compute this M guy, that is not really very directly helpful to an experimentalist. An experimentalist will have to do some extra work to get to the number that he or she will need to check against their experiment. So of course, to help out our experimentalist colleagues, we should just compute the number directly ourselves. And that is what is called, so what we computed is called a polarized amplitude. Okay, polarized because all the spin states and the polarization states are specific. But what we should really compute to help us, our experimental colleagues, is the unpolarized one. Okay, so the unpolarized one is something which, if we compute, that will match with the experiments directly without any further intervention. And what is this unpolarized things? Well, we have to average over the initial spins and polarization because we do not have control over how it is being prepared. It is completely random. So we just average over all initial spins and all initial polarization. And then we sum over final spins and polarizations because the detector is going to detect all possible outcomes. So it's going to detect whatever is the outgoing spin of the electron. It's going to detect the photon, whatever is the outgoing polarization of the photon. So with this prescription, and this is essentially, so whenever you do average of a spin, so there are two spin sets. So for each spin, so you have to do this half spin, and there are two polarization states, so you have to do this half polarization thing. And the final spins, you just sum over them. So this is just spin, and then this is just sum over the polarization. So these are the things that we have to do. Okay, so we have to basically, this boils down to doing 1/4 sum over S prime, and then sum over I and J. 1/4 because of the two half in the two averages. So whatever M we have computed, or M squared that we will compute from that M, on that M squared, we have to do this full sum with this 1/4. That will give me the unpolarized matrix elements. And that will be something that we can directly use to compute a number that we can compare with experiments.
Of course, this you're doing in QED, you could have more spins and more polarization.
This is something that this discussion is independent of QED. You can imagine going into some other theories where you have other spins and everything. So of course, for scalars, you don't have to do this, right? Because scalars have no polarization, no spin states.
Right.
But whenever you have fermions and other gauge bosons or things, then you have situations like this. So if you have a theory of, let's say, two kinds of fermions interacting with each other, then even there you would have needed to do something like this. Remember, I'm not saying that the polarized matrix element is unphysical or anything. It's perfectly physical, but it's just that doing that specific experiment for which that is an answer might be a difficult experiment. It's not technologically, might not be always feasible. So sometimes what you need to compute is this unpolarized thing, which is technologically much easier to do. So both of them are physical observable. Which one you should compute, whether you want to have to do this extra step or not, depends on whether this particular process can be done in a very controlled way or not in a controlled way in the experimental setup or not. That's the crux of it.
Okay, thank you.
Okay, so this summing over the spins is something that is very easy. And this is something that you should have already seen in the fermion clauses. that if I sum over the spin, the identity that is going to help me doing this spin is that whenever you have USP, US bar P, this we can just replace by P slash by M plus M. Okay, this is how the sum over spins is going to be done for both S and S primes. The thing that is new and the thing that we have to discuss is that what is going to help me do the sum over the polarization. So I'll have to do something like this, right? I have to do epsilon mu I, maybe this has a bar, and then epsilon mu I. What is this? I'll need to do some sums like this as well for I and j. And this is the second point, and we will see that word identity will help us in figuring out the answer to this question. Okay, word identity will help us. But is it clear that why we need to consider this unpolarized matrix element square?
Yes, it's clear because
Okay.
we can't control the initial state.
Yeah, good. So now let's see that how word identity helps us in summing over this photon polarization. So once again, we do not have to stick to, so this prescription is universal. So you do not have to stick to the specific Compton scattering. So for just the next 5 minutes, let us consider a general QED scattering, which I have denoted by this diagram, that there is the solid lines are fermion lines, could be electrons, could be positrons, and the wavy lines are external photon lines, incoming, outgoing, all sorts of things. And we are essentially interested that there is one external photon with momentum k. Okay, and then it has some it's an outgoing photon according to my diagram. So it has some polarization which is going to be epsilon bar I. Okay. And let's, so with this, I mean, we know already that I mk, the amplitude, I can write this thing as some m mu k, and the photon line, I can write it explicitly epsilon mu k. And then I need to compute the amplitude square, right? So this is going to be mod epsilon I mu m mu squared. And from there, I need to compute the unpolarized one. And to do that, I have to sum over the polarizations. So here I have to sum over the polarizations. And then I'm going to expand this thing out, and I'm going to write this thing as summation I epsilon bar I mu k epsilon mu I k m mu of k m bar nu of k. Okay. And now we can stay fairly general and derive the rest of the things, but the fastest way will be to choose a specific coordinate. And let us say that this outgoing momenta is going along the z-axis. So we choose the momentum
Would that
like
have a
this.
power of 2 on the left-hand side?
Yeah, this is a square. Yeah. So we choose the momenta going along, photon going along the z-axis. And then we choose the polarization to be the linearly polarized one. And then with this choice, this just simply boils down to m1 k squared plus m2 k squared. Okay. Now, this is perfectly fine. This is just me writing down a general amplitude in a specific choice of polarization and coordinate frame. But now let's use the word identity. And what is word identity telling us? It's telling me that k mu m mu of k, this has to be 0. That's word identity. In this specific choice of reference frame, this tells me that k m0 of k minus k m3 of k, this has to be 0. And since the photon definitely doesn't have 0 energy, so k is not 0, that means that m0 must equal m3. So if M0 is equals to M3, then to this line here, I can add a mod M3 square. And I can subtract a mod M3 square, but since M3 is equals to M0, I'm going to think of this as M0 square. So I just added and subtracted off the same things. So basically I've added 0. So all I'm saying is that M unpolarized squared, this is mod M1 squared plus mod M2 squared plus mod M3 squared minus M0 squared. And this is nothing but minus eta mu nu, M mu k, M bar nu k. So now compare this, and it tells us that as long as epsilon nu is contracted with, sorry, there should have been a bracket here. As long as the epsilon mu and epsilon nu are contracted with M mu and M bar nu, this summation over I epsilon I, this thing can be replaced simply by minus eta mu nu. So the rule of thumb is that sum over I epsilon mu I k epsilon nu I k, you can replace this by minus eta mu nu. This is not an equality, mind you. You can't prove the left hand side is equal to the right hand side. That's not true. But whenever you have this combination with contraction with the amplitudes, you can just simply replace this sum as minus eta mu nu. Okay? So that's why I wrote it as an arrow. It's a replacement rule. So this is how the sum over the polarizations is going to be done. And once we do this thing, we can very easily write down the final answer. So there'll be some steps of straightforward, but initially it might seem like a little tedious algebras that gives you that if you do this sum over the spins and the polarizations and the average over the spins and the polarization, you get this expression. So I'll leave it to you as an exercise to do these steps, because there are other steps that we need to do after this that we want to discuss in more details. And this whole big, huge expression, I'm going to write in this form that, so basically we are multiplying this whole thing out, right? So this has two terms, this has two terms, this has two terms, this has two terms. So when you multiply this whole thing out, you're going to generate a lot of terms. But essentially, you see that you can classify them by the denominator. So whenever you have, let's say, this multiplying this, and multiplying this, you're going to get something which is p1 dot p2 squared. So that's the first term. Okay. Similarly, whenever you get multiply these other combinations, you will get something which is p1 dot p2 and p1 dot p4. So all numerators are collected into something that I'm calling t2. Then you multiply, you get the other combinations p1 dot p4 and p1 dot p2. That we are calling t3. And then p1 dot p4 squared is t4. So now t1, t2, t3, t4, these are really not independent, as you can already guess. And in fact, t2 and t3 has to be exactly the same, because they are related by just simply, trivial changes. So they are essentially same. You can also explicitly verify this thing. And T1 and T4, these are related by simply changing P2 to minus P4. So in T1, once you have found the expression for T1, if you just simply change P2 to minus P4, you will get the expression for T4. So you really don't need to compute T1, T2, T3, T4, all four separately. You just need to compute two, let's say T1 and T2. So if you compute T1, from there, using this simple rule, you can compute T4. And once you have computed T2, that's exactly equal to T3, right? And all of this involves some complicated traces over many gamma matrices. But, and each of these traces, naively speaking, will have 16 total terms, but not all of them is going to contribute. Among the 16 terms, half of them is going to have exactly even number of gamma matrices. And the other half, so the other 8, will have exactly odd number of gamma matrices. And what do we know about trace of odd number of gamma matrices? we know that the trace of odd number of gamma matrices are precisely 0. So T1, for example, is going to be this term, this specific term. When you expand this thing out, so I'm saying, so if you expand this thing out, like here, for example, this has odd number of gamma matrix, right? There's only one. This one has odd number of gamma matrix. There is 3. This one has odd 1. This one has odd 1. This one has 2. This one has 3, and this one has 3. So when you multiply this whole thing together, depending on whether you're multiplying with one with M or whether one with gamma, you will get something which is odd or something which is even. So 8 terms have even number of gammas. So this we need to evaluate, but 8 terms will have odd number of gammas. And this we know that we don't need to evaluate, because trace of any times you have a trace of odd number of gamma matrices, this is identically 0. So in this big expression, actually half of the term you don't need to compute. Half of them are identically 0. So you just need to focus on the ones that you get, which has even number of gamma matrices. And then to simplify these expressions, you use what are called the trace identities. So this is something that you have already derived or seen. So for example, trace of gamma mu, gamma nu. This is just 4 times eta mu nu. If you have trace of gamma mu, gamma nu, gamma rho, gamma sigma, then this is just 4 times eta mu nu, eta rho sigma minus eta mu rho, eta nu sigma plus eta mu sigma, eta nu rho. Okay, and then all these properties of traces, like you can cyclic property of traces, you can flip the order of gamma matrices. So use all of those things. And then you will also need the contraction identities. There are many, I'm just writing a few. I'm sure you have the full list somewhere, or maybe you're given it as an assignment. So for example, gamma mu, this is 4 times the identity matrix. Gamma mu, gamma nu, gamma mu contracted. This is minus twice gamma nu. Similarly, if you have gamma mu, gamma nu, gamma rho, then gamma mu, this is
This was
4
in the
times.
P set 3, this contractions.
Yeah. So yeah, I'm sure you have seen these things already. I'm just simply writing down just so just to refresh your memory. Okay, so stuff like that. So you need to basically use these 2 identities to simplify all of these traces. So let's look at one example of simplification of these traces. So in this example, there is going to be one term and only one term which has all 8 gamma matrices, right? So let's just, that's going to be the biggest term. So let's look at that. So the biggest one is going to be, oops. So trace of P3 slash gamma mu, P2 slash, so this is one of the terms in T1, right? Then gamma nu, then P1 slash, then contract with gamma nu, then P2 slash gamma mu. So the first thing to do is that take the P factors out of the trace, because the trace doesn't act on the momentous. So you give them some dummy indices to write the slashes as something contracting with gamma. So you have P3 rho, P2 sigma, P1 tau, P2 kappa, and then I have the traces. So trace, gamma rho, gamma mu, gamma sigma, gamma nu, gamma tau, gamma nu lower, gamma kappa, and then gamma mu lower. Okay. So all I've done is that I've basically unslashed the P slashes. That's it. Now notice that I use the cyclic property of the trace, and then I can just simply take this gamma mu and put it here. Okay, so if I do that, so I'm just going to simplify the trace part now. I'm going to multiply the p's when the time comes in. So the first thing is gamma mu, gamma rho, gamma mu. Then I have a gamma sigma. Then I have gamma nu, gamma tau, gamma nu, and then gamma kappa is alone. But you see gamma mu, gamma rho, gamma mu, this is precisely one of the contraction identities which says that this is just minus twice gamma rho. And this similarly is just minus twice gamma tau. So all of a sudden, the trace of 8 gamma matrices just simply boils down to 4 times trace of gamma rho, gamma sigma, gamma tau, gamma kappa. And now what I'm going to do is that I'm going to flip the order of gamma tau and gamma kappa by using the Clifford identity. So this one I will write as 4 times trace gamma rho, gamma sigma, twice eta tau kappa identity matrix minus gamma kappa, gamma tau. Now I can multiply the momentas here. So remember these momentas are here as well. So P3 rho, P2 sigma, P1 tau, P2 kappa, these were all there. So if I multiply them, now this simply becomes 4 trace of P3 slash P2 slash twice P1 dot P2 identity minus P2 slash P1 slash. And if I multiply this thing, I have 8 times. So P1 dot P2, of course, is not part of the trace. So I can just write it outside. Trace of P3 slash P2 slash. And then I have minus 4 trace P3 slash P2 slash P2 slash P1 slash. But P2 slash P2 slash is nothing but P2 squared, which is the photon momenta, which is 0. So this is the only answer. And this trace of 2 gamma matrix is extremely easy to do. I'll leave it to you, and you will get 32 times P1 dot P2, P3 dot P2. So this what is the biggest term in T1? This is how we simplify. Everything else is going to have fewer than 8 gamma matrices, but all of them can also be simplified similarly. Okay. So we are not going to, of course, simplify all of them here, but I hope that by now all of you have the confidence that you can just go ahead and simplify this thing. And when you simplify this, so let me give you the answer that you should find. So for T1, you should find that it's 16 4 m to the power 4 minus twice m squared P1 dot P3 plus 4m squared P1 dot P2 minus twice m squared P3 dot P2 plus twice P1 dot P2 P3 dot P2. So the last term is the one that we found. 16 is outside, so multiply it in with 2, that's 32, that's the term we found. Okay. The other ones are much easier than this. Now, similarly, you can find T1. Once you have found T1, remember, we can easily find T4 by simply changing the rule. P1 goes to minus P4, or P2 goes to minus P4 rather. And T2 and T3 you can find similarly. So there is another way of writing this thing. So you can always write in terms of the dot product of the momentas, or you can use the Mandelstam variables. So S, T, and U. So here, S, T, and U, this will be twice P1 dot P2 plus m squared, or this will be minus twice P1 dot P3 plus m squared, or plus twice m squared, it should be. And then U would be minus twice P4 dot P1 plus m squared. So you can write in terms of Mandelstam variables as well. So for example, in terms of Mandelstam variable, the expression looks a little shorter. So this looks like 16 twice m to the power 4 plus m squared s minus m squared minus half s minus m squared u minus m squared. So this is T1. And how do I get to T4? Remember, I need to exchange P2 to minus P4. That essentially means exchanging s with u. So T4 is just simply 16 twice m to the power 4 plus m squared. So s becomes u, so this becomes u minus m squared. And s becomes u, this last term is actually goes to itself. So this is just s minus m squared, u minus m squared. And you can similarly evaluate T2 and T3. I'll leave it as an exercise that this is -8, 4m4 plus m squared is minus m squared plus m squared u minus m squared. And finally, let me also, so now you have T1, T2, T3, T4, put it all together, just do few lines of algebra and then unpolarized mod squared. This is essentially twice e to the power 4. So let me give it to you in momentum form, and you can convert into Mendelssohn variables yourself so that you get some practice with that as well. So P1.P2 plus P1.P2, P1.P4 plus twice m squared 1 over P1.P2 minus 1 over P1.P4 plus m to the power 4, the same thing all squared. Okay. Now note that this is manifestly Lorentz invariant. I don't need to do anything. I don't need to check anything. Every index is completely contracted. It is written only in terms of 4 vectors or scalars. So this is manifestly Lorentz invariant, and this is exactly as it should be, because we spent a great deal of effort to ensure that we are working with a formalism where Lorentz invariance is kept manifest. And that's the payoff, that whatever calculation you do, you don't end up with something for which you have to check that the Lorentz invariance is not manifest. So I have to check by hand that whether it's still there. And that is the difference from the other approaches. If you had done using the other approaches, you will get an expression here at this point, which will not look manifestly Lorentz invariant. Of course, it will be, but it will not look like that. It will be written in terms of components and stuff like that. And then you'll have to explicitly, painstakingly check that whether this is still Lorentz invariant or not.
And that makes calculations in higher dimensions more easier.
Not higher dimensions necessarily, but higher loops. So when you go in higher ordered imperturbation theory, this of
Right.
course, I mean, even in tree level, you can already see that this is not really a short 2-line computation, right? This is, if you spell out all the details, this is going to fill out pages after pages. So for example, here, if you mess up somewhere and you get some index which is not contracted, then you know that you have messed up somewhere, that this is not supposed to have a free index. So you can go back and easily find it. But in the other approaches, it's much harder to do that because you don't know which step you have messed up.
Yeah, it tells you if you make a mistake. Yeah.
Okay. So this is my the matrix element squared, right? And then with this, we are now ready to compute the differential cross section and then integrate it to get the total cross section and stuff like that. And now typically, of course, you can, if you want to compute the differential cross section or total cross section, you will have to pick some frame, either the lap frame or the center of momentum frame, whichever is the natural one for the context, either because you're trying to give a number which can be directly checked against an experiment, or simply because you're trying to give a number which you have to check against some other calculations. So whatever is your end goal, depending on that, you will choose a frame, and you will have to do the computation. So let's first pick the lap frame. And the reason for that is that this scattering historically, when it was first being performed in 1920s, and then it was also around the same time when these formalisms were being developed. Of course, not Lorentz covariant or Lorentz invariant quantization, but the first way of doing electromagnetism and interaction with matter was being developed. People naturally assumed the lap frame framework, and the lap frame framework was essentially this, that you have the electron which is at rest. So the initial electron, the incoming electron, and this is at rest, that's the lap frame, right? And then you hit it with a photon. So there is a photon, and we have taken our axis such that the photon is going along the z-axis. It comes and hits a static electron. And then, of course, once it hits, the electron sort of goes in one direction, and the photon goes off in another direction. And we have just labeled that the photon is going off in the theta direction, so its components are going to be like this. And P3 is going to have some components which going to look like this. And all of you are have enough experience that how to convert these things into this standard kinematic consideration. So for example, P3 squared, this is m squared, right? But P3 squared is also P1 plus P2 minus P4 whole squared by momentum conservation. And that tells me that m squared plus twice m omega minus omega prime minus twice omega omega prime 1 minus cosine theta. So m squared is equals to, so this is equals to m squared, let's say. Okay, so this m square cancels, and I can simplify this thing, solve, and I can write 1 over omega prime minus 1 over omega is equals to 1 over m 1 minus cosine of theta. This relation we can, so typically when you have this relation, you want to solve omega prime in terms of omega. So what is the energy or the frequency of the outgoing photon in terms of the incoming photon and the angle, the scattering angle. And then when you solve this thing, you get an expression which is omega prime, omega divided by 1 plus omega over m, 1 minus cosine theta. So does this formula seem familiar to anyone? No, probably it has been too long since you have studied this thing. So this is really the formula that you would compute using the standard relativistic scattering, and this is the Compton's formula for the wavelength or frequency shift. Okay, so this is a computation you must have done in your undergrad days. And then we have to integrate over this mod m square over this, what is called this Lorentz invariant phase space for the 2 to 2 scattering, which is usually denoted by pi n if it is n to n scattering or 2 to n scattering. So this is what we say d pi 2. And just to remind you, the definition of this is that, so the outgoing moment P4, 2 pi cube, its energy, so 1 over 2 omega prime. Then I have integral over the outgoing electron, d3p3, 2 pi cubed, the energy of the electron, so 1 over 2 e prime. And then I have the momentum conserving delta function. And this is a straightforward integral, just a few lines. I will leave it as an exercise for you to check that this is precisely 1 over 8 pi integral d over cos theta omega prime squared by omega times m. Okay, so once you have this thing, the differential cross section is very easy to write down in lab frame. So d sigma d cosine theta. So this is lab frame is just 1 over 2 omega, 1 over 2m, 1 over 8 pi, omega prime squared. So this is just the Lorentz invariant phase space factor, and then the m unpolarized square that we computed. And now, if you go back and use this P1, P2, P3 parameterization and put it back into this expression of m unpolarized square, you can check for yourself. It nicely simplifies this to pi alpha squared. So alpha is the fine structure constant. This is typically normal, that the coupling is written as this dimensionless quantity squared by 4 pi. This is the fine structure constant. So coupling constant of QED is taken to be this alpha, not E, because every time you won't have a process with just one E. You will always have a process where there are things coming in pairs. So this is a better way of counting it. So pi alpha squared m squared, or not alpha squared, this should be, I think. Yeah, okay, fine. Omega prime by omega squared, omega prime by omega plus omega by omega prime minus sine squared theta. And this relation, this lab frame expression actually was first derived in 1929 by Oscar Klein and Nishina. And it is a very famous relation, which is called Klein-Nishina relation. And this is the modern derivation of it. Okay. Now that's the lab frame result, and lab frame result is extremely useful when you are trying to compute the answer with which the experimentalist can directly measure. So now the experimentalist, can integrate this thing, get the total cross section, and they are ready to directly compare it with their experimental data. But sometimes for some other considerations, sometimes it's okay to look into the other frames. But before we do that, maybe let me just point out one more physics that comes out from this. So you can now, once you have derived these expressions, you can now actually do something simpler. You can look into one limit, which is the low energy limit. So what is the low energy limit? The electron was already static, so you can't make its energy any lower. It's already at rest. So what you can make lower is the incoming photon's energy to be lowered. So let's say that omega tends to 0. But from the relation of the omega prime and omega, you will see that this ratio, however, remains of order unity. And then under this, d sigma d cos theta simplifies a bit more. And it looks particularly very simple, and it's just 1 plus cosine square of theta. And this is, of course, something which is a very old result, because this is like static electron interacting with very weak pulse of light. And this was something that Thomson computed way earlier. And this is precisely what is called the Thomson cross-section. So we are able to recover this known physics starting from a fully relativistic scattering. Okay, so this is a good consistency check, and this is always a good idea. Whenever you compute something, and in some special limit that is supposed to match with some known physics, it's always a good idea to take the limits and check that whether your answer matches with the known physics or not. So Thomson cross-section was known when Klein and Nishina found their formula. So this is a quick check to make sure that indeed what they have is a consistent thing with the known physics. Now, if you are thinking about the low energy limit, then of course, one should also think about the other opposite limit, the high energy limit. Now, it turns out the high energy limit is actually understood better, not in the lab frame, but going into the center of momentum frame. So the center of momentum frame is where, so the photons and the electron that comes in, they do some collide, whatever, something happens, and then the photon goes out, the electron goes out, right? And the thing is precisely such that it's essentially we are in a frame where this collision is really happening in our frame essentially. So this way of parameterizing is choosing, let's say, P2. P2 is the incoming photon, so let's choose it to be the same as in the z-axis. So P1, then we have no other option but to choose. So we have to cancel the momenta. So we'll have to choose this minus omega, and then whatever energy I need to give the electron to make sure that it satisfies this is I'm calling E. And then P4 will have some same energy, but omega sine theta, 0 omega cosine theta. And then P3, it's fixed by conservation, right? So I'm not writing it down. You can find it for yourself. But what is really needed for the high energy limit is the dot products, the Mandelstam variables. So P1 dot P2 here will be just omega E plus omega, and P1 dot P4 will be omega E plus omega times cosine theta. and E squared will satisfy omega square plus m square because of the mass shell condition of the electron, that P1 squared is m squared, right? And now we can discuss the high energy limit in this frame. So far we have not taken any limit. We have just changed the reference frame. We have changed the reference frame where the momenta of the incoming photon and the incoming electron are exactly equal and opposite. So they are head-on colliding, okay? So maybe a better way of drawing the diagram would be something like this, that the electron comes in like a solid line and the photon comes in precisely like this. And then they collide and then they scatter off in some angle. Okay. So what is the high energy limit? So one thing at the high energy limit is that the energy of the electron has to be much, much greater than the mass. So the rest is effectively, like, the electron is given so much energy that it's way bigger than its rest mass. Okay. Now, if you really send in the electron, the initial electron with this much energy, it's coming with a huge, 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 huge amount of energy and it's head-on colliding with a photon. What do you think is the most likely possibility that when it scatters, what is the angle with which the photon should scatter?
Zero degrees?
So let's say, yeah, maybe I've drawn the diagram in a bad way. Yeah, you're basically right. So you basically mean that it will just go back, right? So if it's coming in this way, it will hit and then it will just go back. It will flip and it will go back. So in my ways of parameterizing, I would want to think of this as theta equals to pi. And then once you have this limit, you can show that P1 dot P2 divided by P1 dot P4, this term is the one which dominates over all other term in m squared. So let me just quickly go back to the expression for the m squared. So as you can see that there was a term which was P1 dot P2 divided by P1 dot P4, then exactly its reciprocal was here. And then there are these other terms. So all of these terms are going to be much, much smaller compared to this one. So this is the one that is going to dominate. And we can use these relations that we have written down here to basically write down that the m unpolarized squared is going to be twice e to the power 4 e plus omega divided by e plus omega cosine theta, and which implies d sigma d cosine d cos theta in the center of momentum frame, and in this limit is 2 pi alpha squared divided by 2m squared plus the Mandelstam variable s times 1 plus cosine theta. So this high energy limit is actually quite interesting. There is a very interesting story with this high energy limit, but unfortunately I don't have time to describe all of it because I want to, in the remaining time, point out another interesting physics before we stop. But let me just quickly say what the physics is that if the initial photon has a definite chirality, like if it's a, it's a right-handed photon or a right polarized photon or a left polarized photon, and then when this head-on collision happens and the electron also has a definite spin state, right? It has this like right spin state or up spin state or down spin state. Then essentially what happens is that most of the scattering, which is sort of backscatters, this is called a backscattering. So it's coming in front and then it just jumps back. It exactly goes back. So most of the backscattered photons would actually have the same helicity, but the highest energy photons would be the one where the helicity has flipped. So this is actually something that you can use to either detect the polarization state or spin states of the electrons, or you can use this to sort of find a way to create specific ratios or specific ways of polarized states of photons and so on and so forth. So you can essentially take advantage of this formula. So this high energy limit is a sort of a very useful thing because it tells us that, okay, fine, that if I really send in the electron with a huge amount of energy, then there is this new application of it I can use to do some other things. So before we stop, I want to discuss one more very important property. This is once again general about QFT, but in particular for the scattering amplitude that we computed for this, it's going to have a very nice consequence. And this phenomenon is called what is called a crossing symmetry. So crossing symmetry is essentially the statement that if I have, now this is any QFT, if I have any quantum field theory where there are some external particles, there are some green lines, there is a different kind of external particles, the red lines, and then there is a yet another different kind of particles, which is the purple line. You have situations like this, and then you have the exact same process, but all the things that you have done is that you have essentially changed the purple line by its antiparticle, and you have given it exactly the opposite momenta. Okay, so this u is some particle, v is exactly the antiparticle of u. And if u was coming in with momenta p, v is coming in with the momenta minus p. Okay, or you can think of it as going out with momenta p if you want, but I mean, that's the idea. So crossing symmetry tells us that these two processes, where you take one external leg and you replace it by its antiparticle, but with exactly negative momenta, are actually the same state. So the statement is that m, so let's focus on electrons for specificity. So if I have an electron coming in with momenta p, and then dot, 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 some other states are there, I don't care, and it goes into dot, 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 dot prime in some other states, then this is the same process as this dot, dot, dot going into dot, dot, dot prime plus E plus with minus P. And for electrons, this is actually very quickly, we can quickly see why, because this external electron, right, they will have some factors like USP, and then I will need to take the mod m squared. So I'll have a U bar SP, and then I'll have a sum over the spin, either because these are the initial states, I'm averaging over them, or these are the final state, I'm summing over them. Either way, this is going to just give me P slash plus M, which I can write it as negative of negative P slash minus M. But the negative P slash minus M is nothing but S Vs of minus P V bar S of minus P. Okay, so we have replaced the fermions by antifermions, the U by the V and the P by the minus P. The only thing that is sort of there is this extra minus sign. We can take care of this minus sign as well by absorbing it into the phase of the V. But the most practical thing is to just, remove this by hand. Just remove this, so by hand. But you don't have to. If you want to be more precise, you can just absorb this minus sign into a phase of the V and the V bar. So that essentially implies that any quantum field theory diagram that you have, and if you find a new diagram or a new process which is related by crossing symmetry, then you don't need to do a new computation. And that actually has a very nice implication for us, because let me do this final process. So this process has a name. It's called pair annihilation. And its name is self-justified because it's basically saying that if a positron and an electron meet, they decay into each other into two photons, right? And this process, you can, if you just look at this QED process, you can convince yourself that this is going to receive contribution from these diagrams. So this is P1, this is P2, this is P3, this is P4. So P1, P2 are the electron and the positron, and they decay into two photons. And then you will have another contribution, which will look like this. So this is P1, this is P2, but now I'll have the P4 going along this, and P3 going along this. So I'll have these two diagrams. Okay. Now these, you see that E plus, E minus going to gamma, gamma. And if you had E plus gamma, sorry, E minus gamma going to E minus gamma. So this was the Compton scattering, the second one. If I use crossing symmetry once, right, I can bring this E minus onto the left-hand side, and that becomes E minus E plus, and I can take this gamma to the right-hand side, but the antiparticle of a photon is a photon. So this is gamma, gamma. And now you realize that the Compton scattering and the pair annihilation, they are actually related by crossing symmetry. So you really do not need to do a new computation. So the answer that we have computed for Compton scattering has also immediately told you what is the answer for this pair annihilation, electron positron colliding to annihilate themselves and become photon. So more precisely, all you need to do is that so this is the Compton, this is the pair annihilation. So whatever you called P3 for the Compton, right? This was the outgoing electron. You just call it minus P2 in this way of drawing the diagram, because I gave P2 to be so this one is the positron, this one is the electron. So I called the electrons, positrons momenta to be P2. So this has to be minus P2. And then P2, which was the photon, right? The incoming photon, which is there. And now it has gone into some outgoing photon, which is the P3. And it will go to minus P3. So whatever computation you did with the Compton, you change the level of P3 to minus P2 and P2 to minus P3, you will get, so whatever M you had for Compton, and you do this prescription, you will get an answer for the pair annihilation. The only thing is that you will get this extra minus sign, which I said that, okay, you can just remove by hand. And that's it. So you don't need to do a new computation. So the answer that you have, do this simple thing, and then you have this. So this sort of crossing symmetry is extremely important. It's one of the most fundamental relations in QFT, and it's very useful even for practical things like this. So processes which apparently prima facie looks different actually are related by crossing symmetry. So you don't need to do a completely new computation. Okay, so with this, I think I will stop, especially since this is the last lecture for me. I would like to at least give you the opportunity to ask any question that you may have about today specifically, but also you're free to ask questions about the previous lectures. But I mean, I will first prefer that if you have questions about today's lectures, you ask them first, and then we can shortly discuss the lectures of the last week and the last week.